Across a flat, featureless plain, a monumental steel lattice rises from the dust, marching towards a horizon invisible to the human eye. Its arms stretch outwards, carrying not the familiar thick bundles of telephone lines, but fewer, much heavier cables, humming with a power that could scorch the air. For thousands of kilometers, these leviathans carry an invisible force, linking entire continents and delivering energy born from distant wind farms or hydro dams, yet they do so in a way that confounds the intuitive understanding of electricity. For decades, our entire global grid has been built upon the principle of alternating current, a system so pervasive we barely question its nature. From the outlets in our homes to the power lines strung between cities, alternating current has been the undisputed king of electricity transmission. Its ability to effortlessly transform voltages using simple transformers made it ideal for generation, transmission, and distribution. Yet, in the last 20 years, a different, seemingly older technology has begun to quietly, decisively, replace it for the most critical power links on Earth. These aren't short-haul connections. We are talking about power arteries that span entire nations, cross oceans, or link vast renewable energy projects hundreds of kilometers offshore. For these immense distances, and in these challenging environments, engineers are increasingly choosing high-voltage direct current, or HVDC. This seems counterintuitive. Direct current, after all, was the technology Edison championed, ultimately losing the war of the currents to Tesla's alternating current more than a century ago. The question then becomes, why, after more than 100 years of AC dominance, are high-voltage direct current lines now taking over the critical role of long-distance power transmission, often operating at staggering potentials of up to 1100 kilovolts? What is the unseen trick that allows this old challenger to finally outperform its seemingly superior rival? To understand this shift, we must first revisit the fundamental nature of alternating current, particularly when it travels over vast distances. Imagine a long, powerful hose carrying water. With alternating current, the water isn't just flowing, it's oscillating back and forth, hundreds of times a second. This constant reversal creates problems that are largely negligible over short distances but become monumental obstacles over hundreds, or even thousands, of kilometers. The first challenge is known as reactive power. In an AC system, current and voltage don't always rise and fall perfectly in sync. Inductive components, like the magnetic fields generated by the transmission lines themselves, cause the current to lag behind the voltage. Conversely, capacitive components, like the electric fields between the conductors and the ground, cause the current to lead the voltage. This phase difference means that some of the electrical energy is not actually transmitted to the load but is instead stored and released by the line itself, sloshing back and forth, doing no useful work. This is reactive power. It's like a person trying to push a heavy box by rocking it back and forth without actually moving it forward. While this reactive power doesn't consume net energy, it still demands current flow, which in turn causes resistive losses in the line's conductors. This phenomenon is measured in units of voltampere reactive, or VR, and can account for a significant portion of the total current in a long AC line, severely limiting its actual power transfer capacity. Engineers must install bulky and expensive reactive compensation equipment, huge capacitor banks and inductors, along the line to try and minimize this effect. Even with compensation, it remains a significant drain on efficiency and capacity. A second, more subtle, but equally critical issue for AC transmission is the skin effect. Imagine a conductor, a solid copper wire. With direct current, electrons flow evenly through the entire cross-section of the wire. But with alternating current, especially at the grid frequency of 50 or 60 Hz, the electrons tend to migrate towards the surface, or skin, of the conductor. The changing magnetic fields created by the alternating current induce eddy currents within the conductor, pushing the main current outwards. This means that the effective cross-sectional area of the conductor, the part actually carrying the current, is reduced. It's like having a wide river, but all the boats are forced to travel only along the narrow banks. This increased effective resistance leads to higher resistive losses, often referred to as I squared R losses, where I is current and R is resistance. This problem becomes particularly acute at higher frequencies, though even at grid frequencies, for very large conductors over long distances, the skin effect can contribute substantially to energy waste. Now consider direct current. With direct current, the electrons flow in one continuous direction. There is no phase difference between current and voltage, reactive power simply does not exist. The current flows uniformly through the entire cross-section of the conductor, eliminating the skin effect. For a given power transfer capacity, a DC line can use a smaller conductor, or for a given conductor size, it can carry more useful power with less loss. This fundamental difference is why, beyond a certain transmission distance, roughly 700 to 800 kilometers for overhead lines, or significantly less for submarine cables, HVDC becomes more efficient than AC. While AC suffers continuous, cumulative losses from reactive power and skin effect over distance, HVDC losses are primarily resistive, I²R, and are proportional to length but without these additional AC-specific penalties. The real engineering marvel that has enabled the resurgence of HVDC lies not in the transmission line itself, but in the sophisticated converter stations at each end. Early HVDC systems, dating back to the 1930s with projects like the Gotland Link in Sweden, used mercury arc valves to convert AC to DC and back again. These were temperamental, required significant maintenance, and had limitations in controllability. The true breakthrough came with the development of power electronics, specifically thyristors in the 1960s, and even more significantly, insulated gate bipolar transistors, or IGBTs, in the 1980s. These semiconductor devices allowed for the creation of voltage source converters, or VSCs, which revolutionized HVDC technology. A modern HVDC converter station is a monument to precision power engineering. Imagine a sprawling complex the size of several football fields, dominated by massive, towering structures that look like a cross between a skyscraper and a high-tech fortress. Inside these structures are the VSCs, acting as the bridge between the AC grid and the DC line. At the sending end, alternating current from a power plant or an AC substation is fed into the VSC. The VSC uses thousands of individual IGBTs, rapidly switching on and off, to chop the AC waveform into a pulsating DC voltage. This process, called rectification, converts the AC power into high-voltage direct current. Think of it like taking a rapidly vibrating wave and smoothing it out into a constant, powerful flow. The brilliance of VSC technology lies in its precise control. Unlike older HVDC systems, VSCs can independently control both active power, the useful power transmitted, and reactive power at either end of the line. This means they can actively support the AC grid they connect to, improving stability and even providing reactive power compensation, something traditional AC lines struggle with. Moreover, VSCs can reverse power flow almost instantaneously without reversing the voltage polarity of the DC line itself. This flexibility is crucial for modern grids, where power generation from renewables can fluctuate rapidly. At the receiving end, another identical VSC performs the inverse operation, called inversion. It takes the high-voltage direct current from the transmission line and, by rapidly switching its IGBTs, reconstructs an alternating current waveform that precisely matches the frequency and voltage of the local AC grid. This AC power is then fed into the local grid, ready for distribution to homes and industries. One of the most powerful applications driving the adoption of HVDC is the integration of offshore wind farms. Imagine vast arrays of wind turbines, kilometers out to sea, generating immense amounts of power. These turbines produce AC power, but transmitting this power directly back to shore via AC cables would be incredibly inefficient. Subsea cables have extremely high capacitance. They behave like giant capacitors, constantly storing and releasing charge. This means reactive power losses in AC subsea cables are enormous, making AC transmission unfeasible for distances beyond roughly 50 to 80 kilometers. It's like trying to fill a bucket with a leaky hose underwater, most of the effort is lost before the water even reaches the surface. This is where HVDC becomes indispensable. Power from the offshore wind turbines is collected by an offshore substation, where it is rectified into high-voltage direct current by a VSC. This DC power is then transmitted to shore via a single, or often two, subsea DC cables. Once on shore, another VSC inverts the DC back into AC for connection to the terrestrial grid. This elegant solution bypasses the crippling reactive power and capacitance issues of AC subsea cables entirely. Projects like the Dolwin projects in the German North Sea, handling hundreds of megawatts from multiple wind farms, rely entirely on HVDC VSC technology to deliver clean energy to millions of homes. Without HVDC, the vast potential of offshore wind would largely remain untapped. Beyond offshore wind, HVDC is crucial for intercontinental grid connections. Imagine linking the hydropower resources of northern Canada to the cities of the U.S. Northeast, or connecting the enormous solar arrays of North Africa to the European grid. These ambitious projects, like the planned Euro-Africa interconnector linking Egypt, Cyprus, and Greece, stretching for over 1,500 kilometers underwater, are only viable because of HVDC's superior efficiency over long distances and particularly for subsea applications. Which of these colossal power infrastructure projects would you find most awe-inspiring to witness being built? Tell me below. So, the common-sense guess, that alternating current, being the standard, is always the most efficient, is quite simply wrong for specific, yet increasingly critical, applications. Everyone assumes AC is king, but the engineers have found a niche where direct current is superior, and it's a niche that is rapidly expanding. The actual trick is that HVDC, while requiring complex and expensive converter stations at each end, eliminates the continuous, distance-dependent losses of reactive power and skin effect that plague AC transmission, especially over hundreds or thousands of kilometers, and critically, in the unforgiving environment of subsea cables. These initial upfront costs are quickly outweighed by the long-term energy savings and enhanced grid stability provided by HVDC, especially VSC-based systems. The unseen advantage of HVDC goes beyond mere efficiency. It also offers enhanced grid stability. HVDC links act as a firewall between asynchronous AC grids, preventing the propagation of disturbances from one grid to another. If there's a fault in one AC system, the HVDC link can quickly adjust its power transfer, helping to stabilize both grids. This black start capability, where a converter station can restart an entire grid segment without external power, further underscores its resilience. We are entering an era of global grids, powered by decentralized renewable energy sources. The ability to efficiently transmit vast quantities of power from remote generation sites, whether hydro dams in distant mountains, solar farms in deserts, or wind turbines far out at sea, to major consumption centers is not just an economic advantage, it is a fundamental requirement for a sustainable energy future. The silent hum of high-voltage direct current lines, stretching across continents and beneath oceans, is an invisible testament to human ingenuity, a sophisticated re-engineering of basic electrical principles to meet the monumental energy demands of our time. It is a reminder that even the most established technologies can be reimagined and refined to serve new purposes, pushing the boundaries of what we thought possible.